right, welcome to the video on how to calculate the amount of work when you're pumping some sort of liquid out of some type of tank. In this case, we have a conical tank, an inverted conical tank, which means that the point is at the bottom. It has a height of 20 meters and a base diameter of 25 meters, and it contains oil, and that oil has a density of 800 kilograms per cubic meter. The height of the oil is 10 meters. And what we want to do is figure out how much work is involved in pumping out all of the oil out of the top of the tank. Now, don't get yourself too worked up about how we're going to pump it out. We're just concerned about how much work is involved in the process. So, like every other problem we've done of this sort in this unit, the first thing we want to do is get our sample cross-section right here. And so here's our sample cross-section, and of course, if we make delta H skinny enough, the shape of this is a cylinder. And the first thing we're going to do is come up with a formula for the volume of one slice. Now you'll notice the slices are all different sizes or different volumes, and they all have to be pumped a different distance, which is why we're going to just consider one slice at a time. So since this is a cylinder, we know the formula for volume of a cylinder is pi r squared. Let me label r on here. So here's my r. And times the height, and the height in this case, of course, is delta H. Now you've done enough of these problems that you realize that eventually we're going to end up at an integral, and that integral is going to have a dH, which means that my formula for R is going to need to be in terms of H. So the next thing we're going to do is figure out, well, what is that relationship for R? And we should recognize that we're going to be using some similar triangles. So I'm going to trace out one of those triangles in green right there. And for a moment, I'm going to just bring it over here. And here's my other triangle in green right there. So those are my similar triangles. I'm going to bring those over and we'll label them. The top big triangle has 25 meters at the top, and its height is 20 meters. On the little triangle, since I drew it all the way across, it has a base of 2r, and just like labeled in the diagram, its height is h. And now we have a nice simple relationship with these similar triangles where 25 is to 20 as 2r is to h. We want to solve this for r because r was what we wanted to get out of our volume formula. So we solve for r, we divide by 2, we multiply by h, and then we obviously want to reduce this because we notice that everything is divisible by 5, and we get 5/8 h. And so now we've got a nice expression for r, and we're going to be rewriting our formula for the volume. So I'm going to just move this out of the way. 5/8 h is what we're going to put in there. So our volume actually equals pi times 5/8 h, all of that squared, delta H. All right, so the next step, is to get our units in here. So when we're measuring volume, all our dimensions are in meters, so this is going to be cubic meters. Now we're working towards work, and the first step was to get volume. The next thing we can do is change this to mass. So we're going to get the mass of one slice. And to switch it to mass, this is where the density that we were given in the equation is helpful to us. And we see up here that the density is 800 kilograms per cubic meter. And so we're going to be able to take that 800 kilograms per cubic meter and multiply it by the expression we had up above. Pi, I'm going to go ahead and multiply this out. 25 over 64 h squared delta h cubic meters, and then we see that the cubic meters are going to cancel, and our units are now in kilograms, which is good because that's the unit for mass. So I've got volume, then mass. The next step is to change my mass to force, and we're going to use the force of gravity to do that. So for the force on just one slice, so force on one slice equals 9.8 meters per second squared times the 800 kilograms we had up above. times pi 25 over 64 h squared delta h. And all of that was in kilograms. Good. Now, if you remember, if we combine kilograms and meters per second squared, we get newtons. And that's good because we want force times distance. Our force is in newtons, and our distance is going to be measured in meters. Now that we've figured out the force on one slice, to finish this out, we also need the distance to pump one slice. So distance to pump one slice. So we're going to look back up at our diagram, and we're going to look at the slice we had up here, and we're going to see that the distance that it's going to need to be pumped out is the distance from here up to here. And we can see that the total distance was 20, but this was already a height of h, and so we're going to see that the distance to pump one slice is actually going to be 20 minus h meters. Let me also label that on the diagram right up here, 20 minus h. And so now we've got all of the pieces of the puzzle, and we are ready to write our integral. So our integral, we'll get the limits in just a moment. In our integral, we're going to take force times distance. Now in our force, you'll notice we had a whole lot of constants. I'm going to just put all those constants out front. 9.8 times 800 times 25 over 64 pi. So there's all my constants. Not constant was my h squared. So all of that is my force. Now my distance was 20 minus h. And of course the delta h from force becomes a dh. And all that's left is to figure out the limits on this integral. So I'm going to go back up to my picture for that. And when I look at my picture, I look at my slices and I say, okay, for which values of h do I have slices? And I can see that my very bottom slice is going to be way down here at the tip. So I'm going to have this really non-existent slice with a volume of 0 going all the way up to here. So my slices start at the vertex and up to there, and so I can see that my integral is going to go from 0 to 10. So we put in here from 0 to 10. And then with the magic of your calculator, you will get an answer of 40,088,031 joules. Now, I've taught this for a number of years. I'm going to tell you, taking the time to write each step out before you write your integral is a surefire way of getting these problems right.